A very important part of experimental structure dynamics is to measure the frequency response functions that characterizes the system. So in this presentation we will talk about how we can arrange the test object so that the probability for a good measurement is as high as possible. So how can I measure the frequency response functions, and how should I organize the test object setup? That is the issue of this presentation. So first of all, one can ask, is there any ideal test object setup? Yes, of course there is. And well, let us first suppose that we want to measure the accelerance function between the exciting force Fn and the response acceleration Am, and that we want to do this in a specific frequency range. So how shall I do this in a good way? From a previous presentation we know that the acceleration in a particular degree of freedom m gets contributions from all forces that excites the systems. And in our case we want to be able to measure the frequency response function between the force applied to degree of freedom m and the acceleration measured in degree of freedom m. And if we look at this formula here, we see that life would be much simpler if we only had one single contribution from the force Fn. If this is the case, we can simply measure the acceleration Am and the force Fn and take the ratio between these two for a particular frequency and get the result we want. So how can we achieve this situation so that we only have one single contribution? That is the question. So what we want to do is to apply a force Fn and measure the acceleration Am and take this ratio. So this obviously requires that all exciting forces except Fn must be equal to 0. Equal or very close to 0. So how can we avoid this? Well, first of all we must realize that the support, how we support the test object, how we suspend it, will affect this exciting forces, because the support introduces support forces, reaction forces, which when the test object vibrates will create excitation forces, and that will give contributions to the measured acceleration. And this is a situation that we must avoid. So the answer to this problem, the measure to avoid this problem, is to vibration isolate the test object from the support. And we can either choose weak springs or a resilient slab as a support. So in this case, this frame structure is placed on a resilient slab. It could be some plastic foam, very weak and resilient plastic foam. Another possibility is to use wires that are weak in some sense, so you can put vibration isolators, steel springs, here for instance. Well, the idea is to make the contribution from the support forces negligible by vibration isolation. And the rule of thumb here is to make the vibration isolation as so weak that the resonance frequencies caused by the object support, well, by placing the test object on the support, must be lower than the 1/3 of the lowest frequency of interest in the measurement. So if I want to measure the frequency response function above 100 Hertz, for instance, then the resonance frequencies obtained when I place the object on the support must be lower than, say, 30 Hertz. So that gives us then an idea on how weak the support must be. Here's an example. We have this glider, and as you can see here, it's placed in a frame structure and suspended in strings that are vibration isolated with steel springs here. And in this case, the lowest elastic frequencies, resonance frequencies of the glider is around 2-3 Hertz. So these steel springs must be very, very weak.